So that's tokenizing, and it's done. It wasn't very complicated because we had a regular expression library. So now we actually want to turn this into a structured thing. So we need to take a stream of tokens and map them to symbols in the grammar. So non-terminals in the grammar, which means complex structured things. So the terminals that we've got already are these things starting with T, and they all correspond to a regular expression. And that's going to be the output of the tokenizer. The non-terminals are going to be these structured complex things which are not regular. And you can tell that they're not regular because they're not right linear, and they are recursive. So for example, a factor depends on an expr depends on a term depends on a factor, and a factor depends back on a factor. So they are recursive things. So the kind of parser we're going to build now is what's called a recursive descent parser. So it's used for very simple grammars or occasionally for very sophisticated grammars. So for very sophisticated parsers, so hand-tuned C++ parsers might be recursive descent, for example. This is an example of a top-down parser, so we start at the most complicated thing, and then we actually recursively expand it until we hit the leaves, which are the terminal tokens themselves. Later on, we'll see bottom-up parsers, which work from the tokens towards the roots. So the design for this parser is going to be very, very simple. So the parser is going to take an array of tokens, which was produced by the Lecture, and I'm going to write a series of functions. So for each terminal xxx, for example, Expr, I'm going to call a function called pxxx, for example, pexpr. And each of these is going to look the same. The inputs is going to be our original array of tokens, so all the tokens we know, and the position in that array of tokens where you should carry on parsing. What's going to come out of that is a pair, so this thing called results, and it's going to consist of the symbol representing the entire parsed thing, and the second thing is going to be the next token that follows this in the stream of tokens. If we don't match anything, we'll just return empty or none or null. We'll just return nothing. So the first thing we're going to do is take our existing tokens and bring them from Lecture world to parser world. So if we're parsing an identifier, we have our array of tokens, and this is where we are currently working. If the index we are currently working at is beyond the end of the tokens, return nothing. We cannot parse beyond the end, so we fail to parse and we return null. So if we now look at the actual token and we look at the type of the token, we are trying to parse an identifier. If the type of it is not identifier, we fail to parse and we return nothing. If we pass both of those things, we do have an identifier, which means we can create a symbol, so a parser level thing, and all we do is we bring that Lecture level thing, so the raw string in, and it now becomes this more strongly typed name. We have correctly parsed something, so that means we can return this symbol. That's the result of parse an identifier, and the thing that should be parsed next is simply the next token along. A number is very similar. If there are no more, if we're off the end of the token array, we cannot parse a number. If the type of the current token is not a number, we cannot parse, we return nothing. Otherwise, we take the raw string value and we actually turn it into something more semantically useful, so a number. And again, we return a symbol which has a type and a value. This is the high level symbol we've matched, that we've parsed, and the next thing is just index plus 1. We can do some helpers here, so we've got lots, well not lots, we've got a few of these things like left bracket, right bracket, plus, times, all of these things. We might as well write a little helper function. So this is like a meta parser, so it has part of the parser interface and also a sort of meta parameter. Which symbol should this thing be parsing? So just as before, if we're off the end of the tokens, we cannot match. If the type of the token doesn't match the type of the token we're looking for, we cannot match. Otherwise we return a symbol index +1. And given this helper function, we can now much more easily say a parser for a left symbol is this helper thing, and it should be a left. Parser for a right bracket is going to be matching a right bracket. So it just makes things a bit simpler, avoids repeated work. So that was all our terminals. We can now look at the non-terminals, and these are going to be a bit more complicated. So here is a parser for an expression. It has exactly the same interface as before because all our parsers have the same interface. The possible productions it can use are a term, an add, and an expression, term, a sub, or an expression, or it can just be a term. So all we'll try doing is try this, then this, then this in term. So here is a function that will try to parse an expression as term, add, expression. I don't care how it does it, but if it matches, we should return that match because we successfully parsed an expression by parsing term, add, expression. If that fails, we can try to parse an expression as term, sub, expression. If it matches, we return. Otherwise, the final thing we try is, okay, can we parse it as a term? If we can, we return it, even if we can't return it, because if this thing fails, we have failed. So that's all we have to do for expression. For the term, we do the same thing. So a term can be a factor multiply term, it can be factor divide term, or just a factor. And we do the same thing again. We try the first production. If it matches, return it. If it matches, return it. Otherwise, this is our last effort. Just try and return this thing. Then we can go into p factor. So this is the final level for our expressions. So it can either be a bracketed expression, an identifier, or a number. So we try going for the bracketed one first. If it matches, return. We try for our terminal thing, and if that matches, we return. Otherwise, the final thing it could be is a number, and whether it matches or fails, we return that. So here is where we've got the potential for infinite recursion in recursive descent. So the problem is that p_expr calls p_term calls p_factor, and p_factor calls p_expr. Originally I had this parser wrong in the slides, and I actually had things so it would actually try to go into term and it would actually infinitely recurse in the slides but not in the actual code. But this one's now correct, and so we won't keep recursing because eventually there's a base case. Eventually we hit brackets in here and we have to stop. So the only thing that can cause an infinite sequence now is an infinite sequence of open brackets, or if we just define our grammar incorrectly, which I think is now correct. So the things we didn't look at is these alternative productions for expression, for example. So one of the things that an expression can be parsed as is a term, an add, and then an expression. So we take the same approach. First thing we want is whatever is on the left-hand side of the expression. That has to be a term. So we try to parse it. If we fail to parse it, we return nothing because it's impossible for us to match this production. If we got a left-hand side and we make it through to here, the thing that should follow this term will need to match plus. So now we start parsing from whatever followed the thing on the left-hand side. If it matched, it was an op, and we continue down, otherwise we fail. So even if we parse the left-hand side, we could fail to match the add in the middle. We start parsing just after the plus operator, and we try and get a whole expression. Again, if we fail to return. And then now we build up an actually more complicated symbol. So the type of this symbol is an expression, but now it's an expression with a left-hand side which can be anything. It can be a complete tree. It's got a right-hand side that can be anything, and an operator that in this case has to be an addition. So this is less interesting. Now when we return our matched thing, we're returning this symbol, which is a much richer data structure. It's potentially any tree because this could be a tree and this could be a tree. And we return the point where we should carry on parsing, so it's whatever came after this right-hand side. Factor mul term is very similar. We have a different production, but again, we try for a factor. If we succeed, we look for whatever came afterwards for a multiplier. If we succeed, we look for a term, and then we return this potentially complicated tree structure. So here is our complete parser. I've included the Lecture, so that's the entire Lecture. A file called parse terminals, which contains an identifier parser, a number parser, and all of these different character parsers. From another file called parser non-terminals, we've got Expr term. So all of these composite things we were just looking at. By the way, if you're wondering why it's parser non-terminals, it's because actually I'm pulling these things out of the actual JavaScript, because this avoids that situation where the slides don't actually match up. So this thing is actually loading this dynamically and then formatting it because it's actually easier, ironically. So we've got all of this stuff and terminals, the composite things. I've got a pretty printer which I'll talk about in a minute. But if I want to parse something, I need to say what my tokens are. So that would be, I want to lex, I know 4 plus 5. Then I want to actually parse that is going to be tokens themselves and start at the first token. So if I try running that, parse is not defined because it's called, it's called Expr, isn't it? So Expr is my root thing, it runs, that's fine. If I print that thing, it's just going to say object, I think. 5 is the next index. If I were to print some.0, I get just an object. If I were to print the type of that thing, I get expression. Because this was parsing an expression, it must be an expression. So what can I do with this sim? Well, I'll do it now. So we can actually print this thing out by taking a symbol and actually walking over all the different things. So if I try printing this thing, it doesn't like that. I wanted that, so I need the first thing. So it actually prints out my expression. And if I say plus x times 10, whatever, it will actually create that thing for me. So it is now structured data. And this is the important thing, that it is structured. So if I change this to times, the tree will change its balance. So it faithfully represents whatever's going on. So what we've got now is the front end for a compiler. We have a Lecture, which splits things into tokens according to a data structure. We have a parser, which does a context-free, parses a context-free grammar and turns it into a tree. So it turns the tree into a data structure as well, the parse tree. So this is the beginnings of an abstract syntax tree, which is a data structure representing a structured program. What we can now do is actually walk up and down this tree and do something with it. One thing you can do, which I just showed, is printing it back out. So the AST contains all of the important information, so the structure of the program, the names, the identifiers, the values, the operations, but it doesn't actually contain anything about the formatting. So what we can do is we can actually walk over this tree and print a program that has the same meaning but doesn't necessarily have the same direct syntax or the same characters. So often these are called pretty printers when they try to actually print something out that looks nice. It's very useful for testing a parser, because if you can parse something and print it back out, you can try parsing it and check that you end up with the same thing. So here is a simple pretty printer. It's a recursive function because it's a recursive tree. And all it does is it says, what is this current symbol? If it's an identifier, print the name. If it's a number, print the value as a string. Otherwise, print whatever it would correspond to. So we actually threw away the information that this symbol was originally an asterisk, and now we actually have to bring it back in. Finally, in these cases, we have the composite structured things. And we actually say if it's an Expr or a term, bracket it for safety, then recursively print the left-hand side, print the operator, one of these, and then print the right-hand side. And this can go back into itself as many times as it needs to. So here I've actually connected all this stuff up. So at the top, if I put things in, I can change them, and it will pretty print things. Here's the AST, here's what comes out. If I put lots of extra brackets, it doesn't know about that. So it strips off those brackets because it's not strictly needed. However, if I put something like this, which is not bracketed, it will bracket it because it's showing us what the structure of this thing is. A possibly useful thing you can do with this is actually to then differentiate things. So again, this is actual code. This is actually coming out of the, this is actually being loaded dynamically into this is real code that executes. So instead of printing things out, I can actually just plug the rules of differentiation in. So if I want to differentiate a number, the result is the number 0. If I want to differentiate an identifier, if it's the thing I'm differentiating with respect to, so x, then it's 1. Otherwise, it's 0 again. And I can go through doing the standard rules for addition, the rules for multiplication, and the slightly more complicated rules for division. But basically, I'm transforming one tree of arithmetic into another tree of arithmetic, except this new one represents the differentiated version with respect to x. So here I've got the same thing again, and I'm applying this function with respect to x, applying with respect to y, and then actually applying it back to itself, because whatever comes out of here is parsable, so I can just parse this or keep it as a tree and differentiate it again. So simple stuff like x with respect to itself is 1, y with respect to itself is 1, y times x is this. And if I make it more complicated, should be able to get, well, one of these parts is actually not completely 0. Another thing I could do with this tree is I could write something that simplifies the tree. So something that walks along and says anything times 0 should be replaced with 0. Anything plus 0 should be replaced with the thing that's added. 1 times anything should be whatever is times by. But once I've got this format of a structured representation, is pretty much, you're not really limited in what you can do with it. You can transform it however you want. So where do we go next? Well, this is only how to build a simple parser. So what we'll look at is better ways of creating parsers, so our friends Bison and Lex. And then we'll look at more useful transformations of trees, so things like code generation.